All right. Hi, Peter. And thanks, Peter, for introduction. And yeah, I'm going to present some machine learning application for permeability prediction using some digital log images and some synthetic work. And also, I'm going to present some of image-related processing being done with some different types of machine learning. So motivation is related to flow and reactive transport. However, we can apply those for many different kind of or science related problem involving some flow and transport. And here I made some example of reactive transport in the presence of typical kind of grains, which is obstacle for flow and transport. In this case, I inject some calcium and carbonate ions, mimicking carbonate precipitation process. So given different reactive surface represented by different colors here, and some of the grains are reactive, others not reactive, we come up with a different product of calcium carbonate ions in solution. And it end up having different precipitation patterns, which give us really complex nonlinear problem in reality. So the two most important parameters for continuum scale modeling is permeability, which represent how media can allow fluid to flow through. The other one is reactive related parameters. So this will really focus on more permeability estimation given different geometry of porous media. And many talks in this workshop already cover this physics informed machine learning. So I'm not going to repeat again, but in general, yeah, physical constraint, theoretical equation, some known relationship usually help us to improve our model predictability as well as applicability of trained model. So we really try to incorporate very simple physical information to better estimate material permeability given image data. So since we are talking about some image data of the natural material, I'm going to show a couple different kind of examples. And so here, just very simple glass bead pack, sandstones, and some carbonate chalk, and shell material. Big challenge of these data set is geometry, and the size and scale and composition are quite different across scales given these examples. And also, if you look at some connectivity, the bottom kind of line showing some of four network model extracted from these images in 3D is quite a different scale and different complexity. So those really are difficult to account for these all the complexity directly. So usually we often get some upscaled permeability parameters, which we trying to estimate using a couple different machine learning method. So here, I'm going to show you a couple of some image processing we are taking to develop some general framework from end-to-end AI framework. And top row showing a couple of original image examples, as I emphasized, shale, chalk, and sandstone. So I put some scale of each images. Here is about 300 nanometers to 1-inch samples. And each sample has different geometry. And this middle row represents some described here as ground truth based on traditional segmentation method. However, it's not really ground truth. But for the purpose of machine learning training data set, we take this as ground truth. And so low imaging showing semantic segmentation result using so-called transfer learning of certain method. Here in particular, we use ResNet with some UNet architectures. And one of the nice of this deep learning-based image segmentation is to recover natural shapes of image better than actual traditional method. If you look at here, this shape, and the other thing is this original data sometimes has a lot of kind of artifact caused by imaging techniques, and you can see some electron charging, some of kind of coding markers. And for manual traditional method, actually, we have to clean out this artifact very seriously to get the better result. And however, I think this machine learning was able to recover those without any kind of pre-processing. And in general, this machine learning was able to recover quite fast, relatively accurately as well. This slide is showing some of complexity across the scale. So in this particular samples, we take about 3-foot long cores, and then we analyze a couple different regions depending on some of our interest. And as you can see, some images, these composable images and microcity images. Based on microcity images, we select certain regions where we really want to further analyze. And this image is showing thin sections. Based on thin section, we did some couple different so-called focus eye and beam SEM images to get more finer scale of images. And usually it's a 3D. And based on this, we reconstructed this 3-dimensional image, which has been used for many different purposes. One of them was what scale we really need to take these samples for estimating some physical properties of permeability, some other relevant physics. So we did very rigorous analysis using Postscale modeling. And given this, we tried to regenerate some digital twin data using many different methods employed in typical kind of earth science community. First of all, we use Gaussian model, which basically 2-point statistics-based generation. And since our architecture here is a black represent pore network, it's mostly kind of micro fractures here. This micro fracture cannot be captured by 2-point statistics very well. So Gaussian model, which is really based on 2-point statistics, really wasn't able to generate a nice model. Instead, the multi-point statistics, which can capture some different connectivity and shape, function better. So this multi-point statistics was able to generate relatively nice 3-dimensional framework. In particular, we generate 1,000 cube data set. In terms of quantitative estimate, porosity, correlation, some other characteristics were recovered relatively well. The only problem was we found some artifacts as well as computational expense. It actually took nearly a long time to generate large data set. Recently, we did some so-called specially assembled GAN generative adversarial network framework to generate a relatively large size. And for the purpose of estimating permeability of porous media, we started working with a relatively simple problem first. So we generate a bunch of different bead packing in 2D. And typically, we try to estimate K, which typically used to solve for so-called Darcy equation. This velocity really proportional to certain material properties, which is permeability here and some gradient. And this permeability is typically function of porosity and void fraction and surface area. If you plot permeability versus porosity and surface area, you can see some positive and negative relationship overall. And for the machine learning architecture, we basically utilize relatively simple architectures. For images, we using kind of vanilla type convolution neural network architectures. We use some multi-layer perception, kind of very simple neural network to account for different property values, in particular, in this case, porosity and surface area, and you evaluate different size of architectures as well as how to incorporate this porosity surface area as well. And typically, in this particular case, we generate 345 images. We split into training and testing data set. And then, next couple slides, I'm going to show some of the results we have. And this slide is showing a comparison between some result with porosity surface area as additional physics data and this image only. Apparently, this impact of physical data improved the model prediction quite well. This red line, the black line represent one-to-one perfect line. And then this image only result relatively scattered and also slope quite deviated, and this addition of porosity and surface area improve those aspects quite a bit. If you look at the training data, actually both of them quite performed very well. And this actually large plot showing data result with validation data. We compare this result with porosity surface area versus only one physical data, and so porosity only and the surface area only. And as expected, inclusion of two physical quantity improved model prediction compared to the result with one physical information. Obviously, this kind of demonstration, more information would enhance our model performance in general. And we also compare different kind of convolution neural architectures. We compare ours with some architectures published in Wu et al. 2018. Obviously, this kind of 3 years old kind of literature, so architecture may not optimal for this type of data set particular. But we just compare, see how actually different types of CNN architecture really impact model performance. And our architecture is a little bit optimized for our data set, so it's perform better than previous work as well. We also compare our work in terms of what kind of size information we really want to extract from images as well as these numeric values. And so we changed some size of dense layer and output layers. We showing here that there are some couple optimal architecture size, so which really can be evaluated further with hyperparameter optimization later on. Based on this 2D exercise, we developed some our three-dimensional architectures with three-dimensional data. So this slide is showing how we generate three-dimensional data. So from original three-dimensional data I'm showing earlier from focus dye and beam SEM image set, we generate 256 subset with each has 128 cube data set. Then using race virtual method, we generate permeability values, and we also estimate the porosity surface area using Minkowski functions. And since we need more data, actually, we did some data augmentation by rotating images, so that actually we can improve number of training data. As expected, this three-dimensional original data has more scattered relationship compared to two-dimensional ideal data set. And we take relatively similar architecture to 2D dimensions. So for numeric data, physical data, we make relatively simple neural network systems. For images, 3D image data, we constructed three-dimensional CNN, and then the rest of them quite similar architecture. We concatenated, and then through the dense layer to make some predictor as a regression model. So we try to optimize certain hyperparameters based on our 2D exercise. We are doing some hyperparameter optimization using such as Sherpa, some other hyperparameter optimization tool, but in 3D architecture, really each training time quite long. In this particular case, with one GPU, it took like 6 hours. So we didn't really do many kind of parameter estimation yet, but based on our just limited exercise, we are able to predict relatively well. Actually, compared to 2D, I think this three-dimensional prediction kind of relatively good. In terms of loss values, MSE value, you can see it with physical data. Actually, we are able to improve model performance as well. And since a lot of actually talks covers physics-informed neural network, we also tested some of a simple idea. And I'm not going to take any details. It's covered by several presentations already. For our problem, we really try to estimate very simple kind of toy problem using advection diffusion equation. We have a 2D domain, and then this equation 1 represents advection diffusion or dispersion equation. The equation 2 represents so-called Darcy equation to represent flow field using this material properties permeability here. We compare a couple different cases. So first case, we account for only PDE versus pure data-driven model. And second case, we account for PDE equation, and we estimate velocity with head data. So this involves inverse modeling to estimate a velocity field using observed head data. And third case, we use PDE of advection distribution equation, and we used concentration data as additional training data. And then the last case, we actually combine all cases together. And so this showing some snapshot of our preliminary data. So if you look at data only, we're using actually quite large data points. So actually data-driven model, I have relatively good estimation. This first row showing absolute error map, second row showing predicted concentration field. So
thank you. A couple of minutes.
Yep, I'm almost done. And so if you look at the scale of error map, data-only model predict relatively well at the end of simulation, which is time equal 1. And as we include more kind of constraint and physics, here's a physics equation only, we have a little bit higher. And this PD and Darcy equation where velocity field is not known, so we need to estimate those velocity field from head data. So actually we increase our error. However, by considering additional concentration data for this case, actually we are able to recover analytical solution relatively well for given. We also tested some different types of inverse modeling with a number of training data in terms of collocation point. So the first column showing 10% collocation data, 30% and 50%. Typically, as we have more data, this is kind of initial condition, but as you can see, so middle time and the final time step with more data point as expected, actually, we are able to predict this result. This is more kind of toy problem. However, it's showing that we can formulate physics-informed neural network for the inverse modeling aspect as well. So this is my last slide. So I'm showing some of our ongoing work with realistic cross-media images to predict permeability. Also, we kind of utilizing some physics-informed neural network framework to estimate concentration and velocity field for both for the inverse modeling.